Bhavidhir V. Bharadwaj. Welcome to episode 34 of Genesis of Tomorrow. The following is going to be a conversation about quantum chemistry, artificial intelligence, computational advances, and much more with Dr. Taha Selim, a PhD in quantum theoretical and computational chemistry. Also, folks, if you're interested in such deep science and deep tech conversations and are able to garner even the slightest bit of value from the show, please support us by clicking the subscribe button so that we can keep improving the quality of the episodes and keep on bringing such wonderful guests over for you. And now, without any further ado, let's get right into it. So enjoy and thank you. Okay, we are rolling now. First of all, formally, again, welcome to this show, Dr. Taha. And your work and your experience in general straddles these different and fascinating fields of quantum chemistry and AI. How do you describe this intersection of all these varied fields, and how do you see them evolving? How do you see them evolving from the past to the current times, and then how do you see them evolving in the coming years?
First of all, thanks, Bahaviter, for inviting me and having me on your show. It is an excellent opportunity and an outstanding work, I would say, for you to try to gather ideas and also talk to people from different fields and create this nice synergy. So that's like huge greetings from my side to you.
Thank you.
About the question, the synergy between the domain knowledge and the AI, it's particularly of interest because it's the AI just a smart tool. I mean, you can imagine farming in the past where you need huge labor in order to collect the plants and harvest the fruits and vegetables from the land. However, when you have tractors and advanced machines, you can do this much faster. You don't need this huge, intensive labor work in order to harvest plants and vegetables. So it is the same thing in science. Science is a very complicated work. Science and technology in particular are very complicated works. You need to understand a lot of data set, comprehend a huge amount of data, be able to repeat the experiments, understand the results, try to check and understand and comprehend points from different dimensions and different angles. And typically this is not easy. It might take some time. In some cases, for advanced applications, it might take tens of years, like a decade, few decades. Sometimes it might take a lifetime. And we see this, for example, with the work in battery, the Nobel Prize in battery, or in the work in even machine learning, the Nobel Prize in machine learning, and so on. So what if you can use advanced tools to speed up all of that progress, to finish the tedious tasks for you, not only in science, but also in administration, in HR, and in understanding, collecting data sets, trying to link the dots that you don't need to spend so many hours on it, or fixing bugs that might take from you eats all the night just to fix one particular bug. So you can do so much more if you have these advanced tools like these tractors and advanced machines in harvesting plants and vegetables, for example, fruits and vegetables. So this is what AI is now providing. It's like a smart search, a smart Google that can be able to do a search in real time, but also harvest from the knowledge that have been included in the training, and they give you the answer that you need in a very short time. So you don't need to spend so much time in order to like navigate zillions of websites to search for a particular information. It can come to you at the speed of light in front of your screen. And then you can read it, you can understand it, you can learn faster, and you can acquire the knowledge faster, but also you can accomplish better because you have advanced tools that help you in this, or debugging, scanning a code, or translating code from one side to another. That's also of a particular interest because you might need a month in order to find the tricks to migrate from one programming language to another. But if the AI can do this for you, that's of a particular interest and a great advantage to your side, because it will save the time for you to do this migration. In that sense, AI now in domain knowledge is very helpful it will boost the domain knowledge because you should know about the domain knowledge. I mean, AI, if someone is using AI without understanding what the AI is doing, it's not of a useful tool for her or for them, because now they can just get anything that AI provides and regard it as a state of the art knowledge. But AI is helpful for those who really understand what they are doing. So if you are a software engineer, you are a scientist, you are a research engineer, you are like a developer, and you are using these advanced AI tools, they will be a great asset for you because you are just like talking to them. They can harvest the knowledge for you, and then you can scan what you need and use it toward your advantage. This is how AI is helping and will help in the future by automating things and advancing the domain knowledge, especially in chemistry and physics, where there is a lot of things are involved.
A thing that I recurrently like to do in all these conversations where the subject matter is so dense is ask that ask for ask people to lay out a foundational basis about that subject matter for people who do not really have a technical background. And so I'll be asking you to do the same as well in regards to quantum chemistry and its amalgamation or intersection with AI. What are the key technical things that you feel that the novices should know about in order to enter the entire spectrum of the learning curve of related to the particular subject matter in quantum chemistry?
Okay, that's a great question. I think I can try to answer it from two aspects. One is the current use of AI in chemistry and in quantum chemistry in particular, and the future use of AI and what I personally expect that we should know about AI, or we should use AI or try to adapt the AI to. For the first side, the current use cases are very diverse. It includes, for example, enhancing machine learning models to understand the potential energy surfaces of molecules. Typically, when we study molecules like molecular collisions in space or in the lab, molecules come, they wandering around one another, and they feel one another. And that feeling comes from what we call a potential energy surface. It's like a surface of energy points that's spread around in the space. And using these points, the molecules and their interaction can be described and be quantified as well. So the fit or the having analytical representation of the potential is complicated. So the AI can help in finding a better way to represent the potential, especially when regions are not behaving very well. So there is a bit of randomness, a bit of chaotic behavior exists in these particular regions. The second thing, it can also help in understanding the spectra of molecules. So typically, if you have a telescope and they obtain and record millions of spectra from space, and you would like to resolve that spectra and identify the fingerprints of molecules that you are looking for. So, for example, if you wanted to trace water in an exoplanet, some exoplanet have been observed, and you wanted to say, oh yeah, is this planet habitable? Does this planet have the organic matter on it, so we can regard it as Earth-like planet? And typically for this, you cannot, of course, visit the planet. It's very far, so it's like zillions of kilometers from Earth. However, you receive the spectra with advanced telescopes like James Webb Space Telescope or Hubble telescope, but Hubble now is fading away. But then James Webb Space Telescope is the most advanced now tool in space that have a very accurate spectrometers, especially in mid and near IR infrared spectrometer. So you receive that spectra. So AI can also help in understanding the time series, how the signal is behaving, and try to decompose those signals to retrieve the information from them. So the AI can help in the decomposition of the time series of these signals and resolve them to be able to decode the information that we need. There is also other applications like sorting the chemical data what you need to retrieve, how you can correlate chemical data together, understanding the behavior of molecules and the phase transitions in a much better way. Because AI is not only about generative AI. I would like to explain this because mostly people treat AI as one application only, as a generative AI, like a ChatGPT. But AI is not only generative model; it also includes a machine learning, advanced deep learning, reinforcement learning, and many, many more. And those are already providing great value to physics, but also to chemistry. And they are like also benefit from physics and the chemistry, as we have seen in the Nobel Prize like last year, where it was awarded for the two scientists who have already used the particular Boltzmann dynamics, was an optimization algorithm similar to the way that eigenvalues are defined in order to be able to sort images. So that was quite unique. So I made a bit of video about this, and that was quite fascinating how you can just use this idea of ranking energies in that. So there is this is where AI can help. There is many more, especially in quantum computing for chemistry. Like, for example, there is famous algorithm in chemistry that uses quantum computing called the variational quantum eigensolver. And in that, basically, you wanted to have some sort of a wave function, like a function that describes a state of a system. And then you have a parameter. And that parameter, you usually vary until you achieve the wave function that if you put in a Hamiltonian, a function that describes the quantum system or the molecular system, this wave function should be the ground state, or the one that's correspond to the lowest state that the system can exist in. And that state has an energy. It's called the ground state energy. But if you have one parameter, is fine. You can do it in a classical computer. But imagine now you have a very complicated molecule with many, many atoms. A lot of degrees of freedom are included. Then your Hamiltonian is quite complicated. You need many, many, many parameters to navigate, to optimize this trial function in order to find the lowest. So you are trying to, for example, for the theta, the gamma, the phi, you are trying to lower ones. You are trying to increase ones until to arrive to the optimal value, or the optimization, which is the most lowest value. And AI can help in that by finding the set of parameters that could be useful for this particular application. So instead of making 10,000 runs, you can just do 100 or 200 runs, because the AI has shrinked for you the data sets that you are using, and then tailor it for your application. So the computational complexity becomes less and less. So that's also an active use case in that. So a lot of work has been published by NVIDIA. I have covered it also in one of my recent videos about the origin of quantum information. And because it's all about quantum information, how you can redefine the information that we understand in the universe. And you will find it fascinating that the way that we perceive nature might not be the ideal way. Maybe there is other ways of approximations that can achieve the same result. But we cannot think of it, because either we are too much thinking analytically, so we need something that we can write by a pen and a paper. And if you have a machine learning, we just stack sort of coefficients next to some analytical functions, like those are the bases of the space. But what if there is many, many things? Of course, we started to understand the multi-layer encoding and so on, but the nature might be more complicated than this, or might be too simple that also we cannot grasp this representation in an easy way. So AI can help in that as well. And also there was a recent paper has been published by a team from China and Germany. And that paper described that they have trained a new AI model called the Pi Theos. And that model, they trained it on a quantum entanglement protocol. And typically they can make a experimental setup, where they have those optical gates and the electronics around in a particular setting, and that will generate the entanglement. So this is like entanglement swapping protocol. So they can work with that. However, when they trained it on different types of the setups that they have, and they asked the AI to predict how they can do the entanglement, they expected that one of these setups should be spitted out of the model. So the model should, because it has been trained on this. But surprisingly, they obtained a new way of making entanglement swapping protocol for the two photons. So that was a new way. So we have seen this great value now in many things where AI can even find ways that we couldn't think of to do things. And this also has been done. Similar use cases have been done already in protein folding and understanding protein phases, also in understanding the treatment of diseases using a certain protein or define certain protein structure. So that is a great way of AI. The future side, the coming to the second aspect of this, is a future side of AI. And there we come to one particular interested idea, which is AI can help in defining the way that you would drive the mathematical formulas to describe your system. And in that sense, if you would like to describe a system, that's a bit complicated. It's more theoretical work. It can take a lot of time. From my PhD, I took a lot of time to work with my supervisors on driving a lot of equations to describe, for example, simpler molecular system like CO2. But however, it involves a lot of symmetry groups. There's a lot of couplings, a lot of things that like typically scale up the computational complexity, but also the theoretical complexity way high. And then if AI could be trained to drive Hamiltonians or the mathematical formulas that describes molecular structure in a much more efficient way, that would save time for researchers so they can understand more and more and more.
You talked about very briefly, you mentioned a little bit about quantum algorithms, right? I'd like for you to speak a little bit more about that. How do these different quantum algorithms, may it be quantum variational quantum eigensolvers or the quantum phase estimators, how do all of them actually, on a technical from a technical standpoint, are able to find these ground state of molecules and taking it up a notch, how exactly they can be applied to molecular systems to just computationally find the intractable dynamics between these different things that are happening at the molecular level.
Okay, that's also a great question. Thanks for it. So typically, the quantum computer works differently than the classical. I mean, it's very crucial to understand that the way that we encode information in quantum computing is like profoundly different from classical computing. So we have to stick to this fact. And one of these fundamental differences is that you need to translate your problem into what the qubits can understand. So the fundamental units of information in quantum computing is the qubits. So the qubit is a fundamental unit. So the qubit differs from the classical bit because it has the ability to exist in superposition. So in the default state, it lies happily as a classical bit. It's like sitting in the zero state. But it has the ability that it can transform and become in a superposition of two states, like partly, for example, in state 0 and partly in state 1. So now to map the chemistry problem into the qubits, first we need to encode what we know about chemistry into the qubits. So typically, translation of problem from chemistry to quantum computing is much easier in a sense that you have a Hamiltonian in quantum chemistry, and for qubits you have a Hamiltonian as well. So if you can map what you have as a Hamiltonian, this mathematical formalism that describes a molecular structure for molecules, if you can map it to the qubit Hamiltonian, then you sort of can solve or can find particular results that you are looking for in chemistry just by working on the quantum computer. And how, for example, if we would like to find the energy eigenvalue, the ground state eigenvalue of a molecule, then that's the ground state of a particular chemistry Hamiltonian. We would like to transform this Hamiltonian into the qubit Hamiltonian. And once we do this, there is famous ways to do this, like a particular way. Like we use like a workflow that's, for example, inspired from Jordan-Wigner transformation or parity transformation or these particular things. I mean, they are now built in many software libraries, so it could be used out of the shelf. Of course, the one who running them, they need to pay attention and be able to understand what they are doing. But that once this is happening, you have your Hamiltonian now mapped into what you do on the qubits. And this mapping, it means that this Hamiltonian is now becoming translated into gates, quantum gates. This is what the qubits will understand. And this is the way, perhaps the only way you can manipulate qubits. So either you can manipulate them by a gate that can put them in superposition, or gates that can entangle them, gate that also can perform measurement. So if you have your set of gates, then you need to use what's called the variational quantum eigensolver. And this routine works as follows. So you have your gates and so on. So your Hamiltonian is there, but you don't know what will be the good wave function that correspond to the ground state. So for that, you need a trial function. You need to assume random numbers in a trial function and optimize. Like when you do a neural network optimization, you assume certain given coefficients. Of course, you can make a good initial guess. If you do that, it means that your optimization will become faster. You will achieve the numbers and coefficients that you are looking for much better and much faster. But if not, that's an iterative process. You will keep going until you find the good parameters. So similarly, it is the same. You have your gates and you have your qubits. Then you need to add one or few gates with random coefficients. And those random coefficients typically are angles. So like are random angles on what we represent as a Bloch sphere. Just an angle that you vary. This is your trial wave function. It's just a random function now. It doesn't correspond to the ground state of the Hamiltonian. So typically, and the VQE works, it's a hybrid classical quantum algorithm. So there is hand-in-hand work between the classical computer and the quantum computer. And when you go to the classical computer, you need to update or load these coefficients, these angles, in those like parameterized gates that you wanted to vary, and then perform a measurement. And then this measurement will tell you, did you achieve the lowest energy or not? And then you keep it changing, goes up and down in those parameters until you achieve the most lowest parameter or energy. And this will be your ground state energy. So you vary all of that. Then every time you vary, you execute, you measure. You vary, you load it again from the classical computer. You change the trial wave function, you execute, you measure. Does it correspond to the lowest energy? Yes, no. If no, then you back again, you run, and keep going. So this is a typical workflow that happens in chemistry, but it's also extendable to any other domain. So if you go to finance or portfolio optimization, typically those problems are recasted on a particular Hamiltonian or a qubit Hamiltonian, which if you find this ground state energy of this Hamiltonian should correspond to the optimal values that you are looking for. So that's like a more sketch way of representing graphically the variational quantum eigensolver as one of the examples of quantum algorithms.
One more thing is, how do deep learning models or neural networks are able to model the highly complex but also dynamic interaction between the molecular features and their properties, especially maybe while predicting the reactivity of the entire process?
Yeah, that's also a very good question. It's a fundamental question now that a lot of research groups are working on it in universities, in companies, in research facilities. Like, for example, Google DeepMind. It's also Google DeepMind has a very fundamental work on understanding deep learning applications for molecules. And we can see, for example, AI predictions like used or implemented in AlphaFold. This is a famous now package that can try to predict the protein and the structure of proteins. So the deep learning and AI are in general are contributing there. So in that sense, giving those like available, like commercially available examples, we can think of that deep learning just can give you ways to understand how molecules can evolve in time, because that's a bit of complicated task. You need huge simulations to understand how a water drop has formed in space. It might be simple, but when it comes to water, we are not talking about a protein folding or DNA, or this is like way more complicated in many aspects. But we are now talking about the formation of water. You have oxygen and you have hydrogen, and then they formed water. Typically, to do simulation to understand this and check whether water have been formed in space or in Earth. Of course, now most of theories, and according to my understanding, and also the time that I've spent during my PhD with my contemporary fellows doing work, great work on understanding the formation of water on grains in space. They also were trying to use some sort of prediction models in order to save the time of simulation. Every nanosecond, it might take like a big chunk of time. And then if you wanted to simulate 1 minute or two, that might cost 1 week from your time. Of course, it depends on the facilities that's available to you, but this gives you an idea that this is complicated. So the deep learning, machine learning, and AI in particular can help reducing this time by finding either the phases that you are concerning about. So you don't really need to run the full simulation. You are sampling from the simulation while you are going on the go. Also, they can give you more properties about the structures. The second thing, there is molecules that have phase transitions, like when you do chemical reaction or so. This is where machine learning and the deep learning models are providing great value, because they can help in identifying which phases or which structure you might have during your reaction with time. And this might not be easy to find computationally, because computations might be very complicated or very expensive. And theoretically, also, it might involve a lot of theory, but with machine learning and deep learning, that could be achieved easily. So we can see it now, to summarize, we can see it now in the protein folding and AlphaFold. That's already a working package. There is other works from Microsoft on life sciences and understanding molecules in general. There is research groups who are using already machine learning and deep learning for space studies, like understanding formation of water, but also perhaps some other organic molecules in space. And there is also understanding of the reactivity or the reactive path of molecules, like to compare to experimental results, or to do things in a profound way, so you can get so much more that you cannot obtain easily from theory or from running the computations, because either you need infinite amount of time, or you need theories that might not be at your disposal, and it needs a lot of time to study and to do. So this is where deep learning and machine learning can help optimizing this process and give you some hidden information about your system.
When you talked about a little while back about potential energy surfaces, it is one of those fundamental things that require complex fundamental calculations, right? And a way to approximate these such expensive calculations, you use models like maybe the Gaussian regression, right? Or and most of the times they are facilitated through the means of surrogate AI models. Could you maybe talk about that a little? How exactly these AI models are able to maintain such high accuracy while also being efficient in terms of speed, uh, necessitating all these calculations for these large scale molecular models and dynamics?
That's a very interesting question, and that's also one of the things that we struggle with as computational chemists all the time. It is how to calculate the potential energy surface, how to check that the potential energy surface is correct, but also to check that we have the good analytical representation of the potential. Because after all, the potential is just the data. At some points, you cannot compute infinite amount of points. After some time, you need sufficient amount of points that you can calculate And then if you have an analytical representation of it, it means that you make a fit and or regression, could be linear regression or linear regression, depending on the model. Then that fit should, to some extent, represent with high quality the potential energy surface. So you can use it to even extrapolate or evaluate the points that are not included in the fit, in the original fit. So the workflow of calculating potential energy surfaces is about finding the good method for your workflow. Higher advanced or higher level of theory in computational chemistry requires methods that are very that are computationally demanding. They are computationally very complicated and very time intensive. So the computational complexity is very high, especially with method like CASCF or this particular sort of we are trying to achieve more exact methods. And also the basis set that you are using in order to execute that method, how much the bigger the size of your basis. So whenever they are bigger, they can probe more, they can have more terms to probe certain interaction terms, and so on. So to compute one point for a particular potential, let's imagine you want a high quality potential. You might need, for example, sometimes 2 days or 3 days, with a method like CCC SDTQ, for example, like coupled cluster with single and double and perturbative triplet method. But then you have the quadruple, perturbative quadruple, and then you have the CCSDTQ. And with a big basis, that might take 1-2 days. We're talking about 1 point. If your potential energy surface needs 2,000 or sometimes 16,000 of points, then you would imagine how many days you need to invest in or months in order to obtain all of these points. So the way, if you can reduce the number of points that you want to calculate, that's very optimal. However, you don't want also to sacrifice the quality of your analytical representation, because it's correlated with the number of or the size of data set that you are using in the training of the model. So with advanced machine learning models, you can sort of sample which regions you need some points from. So you can tell, okay, in this region, because there is more anisotropy, there is more variations, I might need more data. But for these regions, I might need less. Sometimes this is obvious because you know it by experience for some cases, but sometimes it is not. And as imagine that you have by a phenomenal power, you could obtain and could calculate all of these points. Then the second problem will be how you can have a good fit for these points. And sometimes the fit might be good in particular region and might be bad or might be of a less quality in other regions. So which also region matters most to your simulation. So machine learning is helping in that. So it can help you to furtherly navigate and reduce the size of the data set you are using in the training to obtain a good fit, but also can guide you about the data and the samples that you need in your configuration space. We call it configuration space. That's matter or relevant to your simulations. So can tell you, okay, you need more points in the short range, because you can use this. You can use models and make the benchmarks to see how this impact your simulation. Does it have a big impact on the final result? Does it have a less impact on the final result? So that's how it is done. And then helps you to find a good way of having an analytical representation of the potential. Then if the potential is chaotic or behaves badly in certain regions because the molecules, for example, come closer and there is huge interactions where you cannot scale them evenly, you have a huge skyrocketing values of energies, but then in a nearby region you have a very low interaction energies, then that's quite contrast that might also blow up your fitting. Then with machine learning models, you can create kernels that can have a good representation for that, and then have this model as your input in your simulation. So you don't need to care about the data anymore. That model even can evaluate the points that have not been calculated. So that's where the business of the potential energy surfaces coming from, how it is done, but also how it benefits from the high level of theory and the personal experience, and also the deployment of machine learning and AI.
Another thing by extension that just correlates to the entire matter is, and also which is one of the arguably the most potent challenge in regard to quantum technology in general, the challenge of noise. How do you mitigate noise and ensure that you're also increasing thereby the stability of the quantum chemistry simulations that we are performing?
That's also a great question of great interest as well. So typically, the workflows that I have outlined are mainly classical workflows. So these are really classical. So they are now executed on a classical computer. When it comes to quantum, we do this business like with VQE, the Variational Quantum Eigensolver, where we do this mapping. We need to translate the Hamiltonians that we are dealing with in chemistry to what the qubits can understand, and qubit understand, or they work with qubit Hamiltonian basically. And the Hamiltonian will describe how these qubits should interact with one another and should be correlated with one another, and so on. But the qubits that we are assuming are logical qubits, so they are perfect qubits. When we are actually having the physical qubits, or the ones that are used in the lab or in the R&D setup in a company, those qubits are not perfect and they have a lot of noise. So you need a sort of a strategist to have an error mitigation scenarios for this. And there is many codes and many ways to do this, like surface codes that have been already published and have been like surfaced by Google recently, and also the Chinese equivalent for Welo, which is Zuchun G3. So that's, I was trying to stick to the Chinese pronunciation of that. Hopefully, still I get it right after saying it many times now on the YouTube channel. So that surface code can help in reducing the amount of noise that are there, but also the error corrections that you need. And since we have all of this noise built in the qubits and the error corrections now, still the ratio between what we can treat as a perfect qubit in our calculations and what we are deal with as a physical qubits, the contrast or this ratio is very high. So it means that to do something useful for a quantum chemistry calculation, you need, for example, 1000 qubit or 2000 qubits. With this ratio, or the current ratio, you need like 20k or 30k qubits in the lab in order to do these computations. So the error correction is trying to reduce this, okay, making a sampling, doing tricks in order to do this. And this has been divided and devised from like 90s, where the surface code has been proposed already in 90s. So that's a very old idea, and it was coupled with topological qubits. So the actual representation of topological qubits came from the surface code. So these are the current tricks that are used in order to reduce the noise and enable us, in particular as computational chemists, but also for doing quantum machine learning and quantum deep learning and other applications, even in finance, in optimization, in logistics. Still, also this would require a huge number of qubits. And even with the current available error correction codes and error mitigations that we have at the moment, you cannot do much like practically useful to the industry with what we have. It's only use cases. So you can tell, okay, I can do this molecules on a quantum computer using 5 perfect qubits. And if you have more, you can scale it up by this method. Or you can do it in a simulator, assuming you have 10,000 realistic qubits and work with it, for example. And that means that you can work with 100, 200 qubits, logical qubits, and try to get value out of this in a simulation. So that's the current state of the art. Still, there is great progress. You see a lot of announcement from every company. There is huge pressure to push the market forward toward realizing the fault-tolerant quantum computer. But that goal by itself is still complicated. So we were trying, and actually we were involved in doing consulting assignments in this, like what you need in order to do this particular problem in chemistry, what you need to do this particular problem in quantum machine learning. And typically, we provide our collaborators and partners, business partners, with what we imagine or what we can calculate as a use case, what would be the limits of this use case, what you need from a quantum computer, and what you can do actually with what is available. Because also, someone can tell, okay, even on academic level, I'm also teaching at university now from Amsterdam of Applied Sciences, and there is many applications that we are using in research, but also in teaching, that we try to do leveraging what's already available out of the shelf from quantum computing hardware. But then we need to bear in mind, we need to include in our mind the noise, the quality of the qubits, and the size of that's available to us. And otherwise, we use simulators. So that's hopefully that shed some light about the current struggle, but also the current state of the art. It's an evolving field. So we have to be patient indeed. But of course, we have to keep close eye on what we can do now and what we can do in 2 weeks, what we can do in a month, what we can do in a year.
Other part of the wagon is when we talk about the matter of scalability. Surely the quantum enhanced molecular dynamics simulations are leading to advancements and innovation, even to a large degree, in simulating these biochemical workings even. But in regard to multiscale modeling, how do we ensure that the quantum mechanics that we are using for small molecules scales up to larger systems in the classical molecular dynamics simulations?
So that's an interesting point indeed. There's always problem about what's your upper limit, what you can achieve in simulations. Theoretically speaking, the sky is your limit. You can have Hamiltonians for even very complicated molecules. That sometimes you can have it for 10,000 atoms, 20,000 atoms, even for many, many molecules that interact with one another. But the problem is how you can derive these Hamiltonians, how you can be able to have the theoretical formalism of this. And if you find a way to scale this theoretical formalism, how you can do it computationally. Because now the computer has limits. After some point, the computer, you have a number of equations, you have millions of equations, you have 2 million, sometimes you have 1 billion of equations. But then there is some limit you will hit and you cannot do anything further and you need to parallelize. It means that you need to define approximations. And using those approximations, you can tell, okay, I can now divide my Hamiltonian into many, many parts. And this is what actually typically the work is done. Scientists and developers and theoretical chemists, they try to find ways in which they can decouple and split the work by working with the symmetry, the physics constraints, the parity constraints, anything that's already exists, and they can give you for free out of the shelf a separation or splitting for the big matrices into smaller ones, so you can be able to do them. So this is a current workflow, but then you hit a limit. So then you can tell, okay, for this particular number of atoms, I cannot exceed more using exact methods. I need to use approximations. But then there is a catch. If you use approximation, it means that the quality also of your results becoming less and less. That's not high. So that's something we need to pay attention to. So it's about the quality, how much you would expect from your approximation to have from it. But then coming to the exact theory, you have a limit, then you use approximation, and then if you hit a limit, You make another approximation, and then you hit a limit. You make another approximation, and then suddenly the quality of the results is gone. So that's classically the hurdle, or the brutal force that pushes people to define ways of like different ways of computing that is different from classical computing, like to do quantum computing, to do things on GPUs, to do things on specially dedicated chips. So in order, or hoping for more computing power so they can increase the size of simulations.
A little while back, and probably more than once, you mentioned about its ability to quantum computing's ability to simulate very effectively the protein ligand binding. In an extension to that, quantum simulations, we know they can assist with drug discovery, right? By predicting all of these things, may it be binding affinities or the protein ligand interactions, as you said, and also molecular docking, right? Three primary things. And as an extension, integrating AI can can also render us to predict to whatever degree the bioactivity of the molecular docking process and the in general workings of howsoever things are working. But how do you see this technology actually advancing drug discovery, and probably a layout, a stepwise layout of how do you see this technology improving in the upcoming years, and to what extent?
So that's also a great point, and a great question, and a great perspective. So typically, drug design is a very intensive task. So you need huge materials and a huge labor cost, but also advanced labs in order to perform the kind of experiments that you need, plus the the legal process and the administration process that's involved, like from getting approvals for your medicine until you achieve the medicine to be approved by, for example, FDA, or to be now sold on the shelves in pharmacies and some medical shops. So this vast, or this work could be reduced by having the digital twin. Like, okay, can you do it in a computer? And this is where the computer aided, like a drug design came in, where can you use a computer to simulate or do the digital twin of what you would like to achieve from the chemical synthesis of the drug itself, but also the effect on the patient. So you can have a patient simulation, and that patient simulation would mean that you can now test the drug on the computer, so you can reduce the number of trials that you would like to access, or the number of people that you would like to access to try your medicine, basically, because you can do more on the computer. So that's a computational task, that's a computationally intensive. So the AI is helping already in that. Can you reduce the size of the trials that is involved in this type of tasks? Can you reduce the computational complexity of the drug simulation itself, like the protein folding, the protein formation, the interaction between the drug itself with the human body, and that things AI can help by technology. But this means that you need also very good chemists, very good startups that work on this, because startups typically have good motivation to do things. Also, they bring fresh minds to the market. When it comes to the people who are dealing with, we find that sometimes, as no voices in the market, you bring more ideas, more fresh ideas than a typical systematic way that have been integrated, and now it's very hard to divert from it. So you have a way, and that way sometimes it's very hard to divert from that way, like where you wanted to go. Do you like to go in this way? You would like to divert from it, and so on. So startups bring good ideas, and you need also customized workflow. So like a particular startup that's focused on a particular solution, so it can help you optimize this solution and have the best out of it. We can see now this was a startup like a DeepSeek in China. It's a good model, regardless of the numbers about whether they used a few millions or few like more. I mean, it's a startup. That's the main aim of that work was only to focus on the added, like the business value of the model itself, how the model can achieve fast results, very good results in a very short time, because it's, and also with less computing power. So that's typical model. And also, for example, IBM has derived and has published a lot of models that are custom made. So for every application, they have an AI model that's really can outperform generic artificial general intelligence dream of models. So that's the idea. So if we can subcontract and migrate the work from the physical lab to the virtual lab on a computer, that would definitely save time and save cost, save human lives, but also save the number of trials and speed up the time consumed to put the already the medicine into the market.
Another very interesting application side of utilizing quantum simulations and AI in general is how they are able, or how they are aiding in the discovery of new compounds, new chemical compounds, polymers, or nanomaterials in regards to material science in general. How precisely do you see this partnership between artificial intelligence and quantum simulation models and technology to enable the discovery of more potent and effective materials in whatever domains needed with tailored properties in specifically two things: first, energy storage, and second, being in the formation of catalysts for different use cases.
So that's also a great application and a great area to navigate and explore the collaboration between AI and material science as domain knowledge. So definitely similar to drug design and the chemistry simulations, AI would help like substantially advance material science and the material simulations. So now so far there is a lot of great work have been done on great works have been done already on battery design, also in the synthesis of sort of coating layers for cars, but also for the space vehicles, like the missions that goes to space, the telescopes, and there is great work where AI already helped in the material design itself. So, and also it would be expected in the future for this to increase. Like I would dream of that AI can help in solving like the Hubbard model, or the reducing the amount of energy you need to produce fertilizers, for example. It's a very costly process, requires a lot of energy and substantial, huge facilities to produce ammonia. And also, second thing is to get rid of ammonia as well. So so you need ammonia to grow the plants, and then you need to sort of recycle ammonia again after what has been done, because there is so much now ammonia, and we are trying. The population is getting bigger and bigger, and of course there is plenty of space on the planet Earth to explore. It just needs bright minds and efforts, so we can work together into exploring how we can turn the great Sahara in Africa into Greenland, for example, like really like a Greenland, not the country Greenland, but into a green piece of land by driving ways of circulating waters or things. Then you technically you are reducing the fertilizer consumption because you have new lands, so there is more to harvest from. And the second thing that will impact the weather forecasting and the weather impact from the pollution that we have, like production of fertilizers, but also the chemical waste, the amount of energy that's produced now. It's, the planet on the high surges than ever. So so that kind of things could be explored with AI, and AI can predict, for example, where to do this particular application. I have seen a lot of application now trying to utilize AI in surface like agriculture. Like if you have a roof at your building, how you can have this and give you an estimation of the impact. If you have like urban, like city, like an urban area of like a major city, you do all of this in the surface, how much temperature drop you can obtain for example, the regions where the heat is very high. But also it can help you like in the watering of things. So you can have sensors, but also you can have smart ways of watering those things. So also you optimize the water consumption, and you don't need human intervention all the time. So depending on the humidity, depending on the weather conditions, the plant growth rate, and the circumstances, those sensors would work hand in hand with the AI driving models to find the good combination of parameters in order to help the planet grow and optimize the agriculture landscape. So that's from a material science and from also agriculture perspective, like it's AI. So the question is how many knowledgeable people we have to do this, and how many people can work together to do this. And of course, as I have said earlier, you need startups and you need people to collaborate from different backgrounds in order to devise a new solution and come up, because innovative solutions would require innovative composition in the team to define that. So that's an open question. Like you don't need like people who are alike to work together. You need people who also are a bit different in order to complement one another in doing something profound and can cause a revolution in the field itself. So AI can help definitely in this if it's also driven by the right minds.
Another question that I have for you is what do you think is a area of work or a frontier that is not as much given as mainstream significance to or attention to? Primarily, what I want to ask you is that what are some relatively undermined or understated frontiers or fields that you feel will be in the upcoming years, are going to boom exponentially and just in general hold a lot of sheer inherent potential in terms of development, which are relatively undermined by the general masses?
Until the general masses. So I think that's presumably okay. So that's very important question, and I would think of now we all as humans are get stuck into the current political situations, economical situations, and all of that. So there is great concern about the politics, like the landscape of economy, but also the political tensions between regions as well. And this pushes the whole world to focus on particular areas like defense industry or cybersecurity or for example fundamental industry related to, for example, chips and maybe mobile phones or having smart sensors or so on. But what usually has been ignored is the agriculture and what people will eat and what people will learn. So the education itself, the agriculture, and the weather and the atmospheric studies are usually ignored. I mean, they don't take much of attention as the current things. Of course, the other situation, the political tensions and the economic tensions, that all in the all histories, it's already there. I mean, but of course, it's usually sometimes too late to start to take care of about the food industry. What if we cannot grow more crops? What if the piece of land that we are using at the moment has now for agriculture has been shrinked by 50%? What will happen? What will happen if the water becoming more polluted than ever? What will happen if the weather become hot in many regions, and then the population will start migrating to certain areas? So that is typically the problem that we have. So I think, in my humble opinion, that we should pay attention also to education, but also to agriculture and water and atmospheric studies. And those are very fundamental cornerstones next to anything like from phones, from computing chips, from GPUs, from medicine. That's also important, because also that's where the humanity needs those things to continue living in the future, and to prevent the population on Earth from shrinking because of the lack of resources. Of course, we have plenty of space on Earth. It just needs smart solutions to achieve or harvest this agriculture power and use it also for our advantage to reduce the pace of the global warming, have more clean water, more clean air, and this will be reflected, of course, on less amount of diseases. So that typically the case. So hopefully there will be some concentration on this in the future, and of course, startups, people, everyone can start looking for solution on this if there is the right momentum and the sustainability momentum. We have in the Netherlands, for example, huge impact for sustainability. Like there is huge support for sustainability. You need to make the urban matters very sustainable, because the Netherlands is not too huge country. It's also very optimized place. It has one of the highest exporter of potatoes. But then with this kind of agriculture power, it comes with good minds in optimization of this power as well. So if this model is scaled to the whole planet, then I'm pretty sure we will not feel the global warming, and the prices of food will get less, and then having more green areas will definitely be helpful for all creatures, including humans.
Your advice for young people, because you come from such a complex matter of study, right? Field of study, quantum technology, quantum chemistry, and then in the same breath, you are able to articulate all these difficult matters for the general masses in a way which is fathomable to somebody who maybe is not a subject matter expert as well, through all your videos and through this entire conversation. Even what would be your advice for younger people who are getting started in their careers, or maybe in colleges right now? What would be your advice for them?
So thanks for your nice words about being wise. I mean, we are all learning. I mean, I'm also learning. I also learn from having a podcast as you. I try also to interview people, but mainly on the industry side, because that's what matters. What also will bring money for people to live in. So you all the time you find everyone has a story, and then you feel like, okay, the only way is to make a story in order, because we are humans, we perceive stories. So tying to your question about the advice for future generation, I would go with, don't go with the hype. So I mean, sometimes people think, okay, now the quantum computing is the highest, then let's now study quantum computing. Quantum computing is a tool to achieve many other things, like to do simulations for chemistry, for physics, for material design, for finance, for optimization, for market simulations, even, and this is all for the greater good. And that's always very nice to have this knowledge, because this kind of domain knowledge is very helpful. Similarly for AI, there is a lot of people also think of interest. Okay, now I need to study AI. I need to be excel in that, because the whole market now is focusing on this. So indeed, and of course, as I have laid earlier, the political tensions and the economic tensions, all history, they do exist, and of course they sort of influence the market to favor some jobs. Okay, yeah, now we have the AI, and the AI is booming in, for example, in certain ecosystem like in the States, but now in China, and we need AI to reduce the number of labor that we are dealing with, and make more profit in companies. And then you get this cycles of in every technology. I mean, like in robotics, robots will replace humans, will not find the human cooker after, and then you try to find which restaurant has a human in it, so you start to go. So, and then we, like now we are using digital radios, but then there is a tendency or a fashion to go to the old these CDs of music, and hear it in the analog way. So that all the time is a tendency for that. So we don't want to feel like fell in the trap of the hype. So, and the most things that need attention in the future is to have better farmers, like equipped with AI knowledge, but of course with the domain knowledge of agriculture, which is sort of now are demolishing because of how the market is driving the workforce, and how the workforce is driven and influenced by the economic and the capitalistic factors. And when we come to this one, then we will have better agriculture industry. We will have better way to grow food, and keep going on the corpus that we have, and preserve the biodiversity. And the second thing is to invest also in the education, where we make ourselves much better. So we have a project in a stealth mode called iCafe, and in that project, which is now a startup in stealth mode, we aim to educate people about the new things that happening in agriculture, in AI, in quantum, in everything, just in a very short amount of hours per week. So what if you have 1 hour only to learn a new thing, and you wanted to cope with this hugely advanced, accelerated market that's happening around you? And that puts a lot of pressure on people, because I cannot learn this. There is no time to learn this tool. The team has adapted this new workflow. I cannot cope with this. My work-life balance is now becoming degraded, because there is no capacity to absorb this knowledge. So in that sense, in iCafe, we are trying to invest in this by using advanced AI power technologies, even so the AI can help, but if it's directed in the good way. So the user, or the knowledge consumer of the website, can learn and engage in a track where they can learn in little time what is happening in the market, but also get skills in that. So we need to invest in that. But what we don't have at the moment is agriculture, because that's a big project, right? That's so you need people to know how to grow food, and grow, like, increase the size of the green pieces of land in the whole planet. So otherwise, we have this global warming, and that will impact the current agriculture areas, and then that will shrink eventually, or potentially will shrink eventually. So, yeah, that two main things. There is other things as well, but yeah, I would say we don't need to fall too much for the hype. I mean, the hype is good, because it's also, this is a job market, but also we need to think on a futuristic aspect and what we need in the future, like food, we need industry, and we need things like this.
I'm really thinking, if I want to go down this tangent, but I will. Okay, how do you actually become a scientist in thinking? Because I mean, one of the most fundamental aspects of being in, or being even related to the domain of science, whichever it may be, is being able to develop the scientific temperament. How does one go about doing that in the kind of world where attention has become such a tough commodity to attain?
So that's a great question. Uh, I've been thinking about this a lot in the past few years, especially before I finished my PhD and after I finished. And one of things that led me to uh, establish the project iCafe in stealth mode, and now we started to organize some labs and quantum labs everywhere, and there is some courses are being in the pipeline. Is that how we can shape the thinking in less amount of hours? Because there is still so much distraction we have from responsibilities, from the daily life work, the amount of meetings that we are engaged in, and all of this puts a pressure on the creativity. So it's I don't want to say it reduces the creativity also sometimes, because the time you spend to think about things becoming less. You need to think very fast, and this is also one of the advantage of AI. It just can help you thinking, so you are not really using your brain. You are just sort of navigating on a higher layer on like some other workers, like some boss oversees what's happening in a factory, but you are not doing the work yourself. So that's okay, that's good, but also that might be potentially bad on the long run also as well. uh, Not because of the technology. Of course, there is drawbacks for every technology, but the second thing is that the time you spend to learn new things that can shape your mind. And your mind here, I mean the analytical mind, and also your mind as a scientist, which is also based on the analytical mind as well. And these things, you need to learn new things in order to think about, in order to correlate how this is related to that. Of course, listening to podcasts, lectures is very helpful, because you can gain so much more while you are doing other stuff, while you are doing driving, cooking, doing sport, walking to the school or to the university or to the work, while you are even taking care of your beloved one and family. But then that's about the listening, but about the practice side, that's where it's missing. How you can practice what you are doing. And this is, for example, what inspired the work I was doing, and also attracted my co-founders to the project, because he shares the same idea, is how to make the education accessible in order to achieve this analytical mind. You cannot squeeze all knowledge in 2 hours, but you can at least increase the level of analytical skills so high so that the learner can develop their own skills and their own mind as well, so towards being a skilled engineer, towards being skilled scientist, and so on. So I would say we need to dedicate some hours in the week to do that. That's for sure. And next to that, we need also to communicate in a much better way. So we need to listen, but also we need to analyze the work and work together, because if you work in assignments, you are learning while you are doing as well. So the idea of a startup is the most good way on the planet, because it's you just put certain people in a room, they are locked down to find a solution. And in that sense, with this energy and with this synergy, most likely they will find a solution. But if you are in a bigger team, like you have 1,000 people, that is very hard that you can talk to one another, because everyone has a different reality to talk about. So I liked one of Clark's example, Clark Alexander, the one he was on your show. He's a very nice person, very smart and very genius. He also has several startups in the States, a close friend of mine, and has very nice vision. And together we are envisioning also producing a book in the future. So I liked his example of talking about the different reality and the different perceptions of people. So if you have now 1,000 people in a room in a company, then you have 1,000 realities. Everyone receives a reality. So the ability to achieve a new solution becoming less, like it will degrade significantly and exponentially down. But if you have 5 to 10, you can achieve a good mind because there is easy to talk. There is way to, can we try this? Can we put it by hand? But if you are in a so much bigger crowded audience, then until everyone is finishing what they wanted to say and doing iterations, the day is gone. So there is not much of this feedback. So the analytical mind is shaped by practice, by doing, by discussion, by receiving feedback on what you are doing. And we will try to do this in iCafe, I mean, to the best we can. That in 1 hour, we'll try to, we have now experimental course that some people have taken, and in 1 hour they could achieve more because there's a way of conversational that's happening. But I mean, that's only one course. I mean, you wanted everyone to be able to do this critics and think for themselves about that. Not only to solve the problems, but to be able to acquire knowledge from discussions and be able to receive feedback and come back to people and so on.
I'm really sorry, it doesn't really happen this much. I do not know what's wrong with my network.
Yeah, no worries. I mean, sometimes it's a weekend and maybe a lot of people are using the network. So that's happening
Right.
also in some places like if you have everyone is now streaming or something, it's make a bottleneck on the network. So
That.
yeah. So I would imagine it's much better in some countries, not because of the internet is also good, just only because not everyone is streaming on
Precisely.
the same time. That
But okay, moving on to the final segment of the show. Dr. Taha, what would be your word to humanity at large?
it's always very hard to say something like this. But I would say we need to help one another. We need to learn from one another. We need also to understand and absorb one another. Uh, so if you are, for example, you travel to different place, you are new, then your personality changes a bit because you are in a new community. You would like to be the best of yourself in this community. But then what if people started to criticize you? Then you will start to enclose yourself. You will start to isolate yourself because you don't want to be criticized much because you are not in your default settings or your default community. But if people start to help one another, then that will be great, because then if you go to a company and then your colleagues are helping you, then you will feel integrated, then you will feel valued, then you will value them as well. So what we need in a humanity, like in a school, if some student came in, if the other colleagues, they don't bully the new kid and they deal with them in a very respectable manner, they collaborate, they start talking, they start to chat, playing sports together, then that will create the best outcome of all humans ever. So I would say that we need better communications. We need to understand that we are different, and this is the beauty about us as humans, that we are different. Otherwise, if we are all identical, we will be robots. That's for sure. I mean, this is the only thing that we would imagine having, because if we are all cloned from one another, either someone cloned us or we are robots. So that's but then because we are humans, then we tend to divert, we have our own personality, and this is why we find some things attractive, because you can travel, you can learn more from different communities as well. So we need humanity to understand this, that by within the way that the culture is diversified and the humans are segmented and have different backgrounds, different cultures, that adds to the total lump sum of the civilization, because there is many civilization can learn from one another. And we can see this in the past where the ancient Egyptian civilization, for example, they have built the Great Pyramids. It was like new discoveries recently, and some hype stories about the ground buildings below the pyramid. Like, so the pyramids are really sitting on pads, but there is some hypothetical stories telling what if those pads, for example, extended to be columns, like the one that the famous columns that we see in that have been already built in the US, but we have this those kind of columns already exist in Paris, in many places in the world, but also in Egypt and everywhere. So that columns, maybe the pyramid is just the tip of that column, and that column extended down because it's like connected to deep down into the ground, and you are seeing the tip of it. So that's a hypothetical story. But you see that these hypothetical stories came out because people are fond of this. Like, there is something different. There is something unique. People were thinking about how we wanted to navigate, connect to the fundamental forces of the universe, how we wanted to connect with one another, how we can achieve a better way of communicating with gods, how we can go to the second life with no sins. These kind of things made that culture unique. And then suddenly you had the Greek culture, where they have learned what they could learn from the Egyptians and then continue their own way onto the fine art of beauty. So the Egyptians were more about the precision, how you can depict the simple and the precise way of like engraving things. But then you come into other hand, the story of the art, how you can like put the most beautiful way of doing stuff, not only the power, but also laying a bit like white statues and having them on a much more expressive ways and so on. So that's also another thing that attracts also us to the Greek culture, to see this kind of gods that have been subcontracted. If you go to China, or to go to the Maya civilization, or you go to India, where also there is a lot of rich history there, or you go to, for example, to China or Japan or Iran or any places in Africa, or there's many ways you can learn, and those kind of diversity, this is what we regard them as a rich history. So we are actually proud of these kind of differences for the past, but we wanted to also to integrate them now in the present. So I understand one another, understand the rights of everyone, and the cultures, communicate, learn from one another, and that will make us great humans in project work, but also in the business, but also on the cultural level, on a human scale, and will make us work together on solving these global issues that we are facing, like the global warming, shrinking of food, pollution of water, and so on. Of course, that's a dream. Hopefully, it will achieve, but at least you have to be optimistic at the end of your podcast.
Certainly. So I think that would be a fantastic note to conclude the conversation on. Thank you so very much to Taha Selim for agreeing to do this conversation, and then just, talking about all the different aspects that you did. And it was one of those conversations where, I think, in regard to the particular subject matter, quantum chemistry and AI, people who do not have a background, technical background, they'll surely be able to have that holistic overview of the entire diaspora and the geography, essentially, of the domain at large, if they go through hearing you talk about all of it. Thank you so very much for doing this. It was lovely, and yes, grateful.
Yeah, thanks very much, Bahavadir, for this nice show and your nice questions, and all the effort you have put in to prepare the questions and navigate the conversations. It's a great work of you. So thanks very much for that. And I would think that the audience already will recognize the amount of effort you have put in this, and as you have put in you have put in the effort in the show, then you get the nice dynamics indeed by that, and hopefully the listener will appreciate the kind of synergy and the energy that you have already put in inside the nice show. So thanks very much again, and I will be looking forward indeed for future meetings and future podcasts as well.
Likewise, likewise. Thank you so very much.